Right now, at this very moment, as you sit there watching this video, something extraordinary is happening in the darkest, coldest, most remote corner of reality that any human-made object has ever reached. A tiny spacecraft, no bigger than a compact car, weighing less than a grand piano, is hurtling through the absolute void of interstellar space at roughly 61,000 kilometers per hour. It has been traveling for more than 4 decades. It has crossed distances so vast that your mind literally cannot process them. It is now so far from Earth that a beam of light, the fastest thing in the entire universe, takes more than 22 hours just to make the one-way trip. 22 hours at the speed of light. Think about that for a moment. Light can travel from the Earth to the Moon in just over 1 second. Light can cross from the Sun to the Earth in about 8 minutes. But to reach this lonely little spacecraft, light itself needs almost an entire day. That spacecraft is Voyager 1. And what it detected at the edge of our solar system has fundamentally changed everything we thought we knew about our place in the cosmos. But here is the thing that most people never talk about. Here is the detail that gets buried beneath the headlines and the clickbait and the simplified explanations. What Voyager found out there was not what anyone expected. Not even close. The scientists who built Voyager, the engineers who designed its instruments, the theorists who spent decades modeling what the edge of the solar system should look like, they were all, in one way or another, wrong. Not slightly wrong. Not off by a small margin. They were fundamentally, profoundly, beautifully wrong. And the ways in which they were wrong have opened up mysteries that we are still trying to solve today. Mysteries that challenge our understanding of how stars interact with the galaxy, how the universe is structured at scales we can barely comprehend, and what it truly means to exist on a tiny planet orbiting an ordinary star in one arm of a spiral galaxy containing hundreds of billions of other stars. So, let me ask you something. What do you think happens when you reach the end of the solar system? Is there a boundary? A wall, a line you cross where suddenly everything changes? Or does the sun's influence just gradually fade, like the sound of music growing quieter as you walk away from a concert? What if I told you that neither of those ideas is quite right? What if the truth is stranger, more violent, more beautiful, and more mysterious than either of those simple pictures? What if the edge of our solar system is not an edge at all, but a turbulent, chaotic, seething boundary zone where the breath of our star slams into the cold wind of the galaxy, creating structures and phenomena that no one predicted and that we are only beginning to understand? And here is something that will keep you up at night. Voyager detected a sound out there. In the void between the stars, in the emptiest, most desolate region any human instrument has ever sampled, Voyager detected a persistent, eerie, low-frequency hum. The hum of interstellar space itself. The background noise of the galaxy. A sound that has been playing for billions of years, long before Earth existed, long before our sun ignited, long before the atoms in your body were forged in the hearts of ancient stars. And Voyager heard it. A machine built by human hands, powered by the radioactive decay of plutonium, communicating with a 23-watt transmitter that puts out less power than a refrigerator light bulb, heard the voice of the galaxy. Let me give you a few facts that will frame just how extraordinary this story is. Voyager 1's onboard computer has 69.63 kilobytes of memory. Let me put that in perspective. The phone in your pocket, the device you might be watching this video on right now, has literally millions of times more computing power than Voyager. A modern smartphone could run every calculation Voyager has ever performed in a fraction of a second. And yet, this spacecraft, with its laughably primitive computer, has traveled farther, lasted longer, and made more groundbreaking discoveries than almost any other scientific instrument in human history. Voyager carries a golden record, a phonograph record made of gold-plated copper, containing 115 images, greetings in 55 human languages, 90 minutes of music from Bach to Beethoven to Chuck Berry, and the sounds of our planet. Wind, thunder, bird song, whale songs, a mother's heartbeat, a baby's first cry. It is a message in a bottle, thrown not into an ocean, but into the cosmic void, on the almost impossibly slim chance that someday, somewhere, someone or something might find it. The golden record is the most distant, most enduring artifact of human civilization. It will exist long after you and I are gone, long after our nations and cultures have risen and fallen, long after the pyramids have crumbled to dust. It may well outlast the earth itself. And here is the fact that should make every hair on the back of your neck stand up. Voyager 1 crossed into interstellar space, the space between the stars, on August 25, 2012. But scientists did not confirm this until September 2013, over a year later. Why? Because the data was so confusing, so unexpected, so contradictory to what every model had predicted, that the world's top space scientists could not agree on whether Voyager had actually crossed the boundary or not. The edge of our solar system turned out to be nothing like what we imagined. It was messier. It was weirder. It was more complex and more fascinating than our best theories had suggested. And that, right there, is what makes this story one of the greatest scientific adventures in the history of our species. In this video, we are going to take the deepest possible dive into the Voyager mission. We are going to start at the very beginning with the audacious idea that launched these spacecraft, the political battles that nearly killed the mission before it started, and the once-in-a-lifetime cosmic alignment that made it all possible. We are going to travel with Voyager through the solar system, planet by planet, moon by moon, watching as it revolutionized our understanding of Jupiter's volcanic moon Io, Saturn's mysterious moon Titan, the sideways planet Uranus, and the wild, windy blue world of Neptune. We are going to follow Voyager through decades of silent cruising, through the emptiness between the planets, as it slowly, patiently, relentlessly made its way toward the edge of the sun's domain. And then we are going to get to the really mind-bending part. We are going to explore, in meticulous detail, what happens at the edge of the solar system. We are going to break down the termination shock, the heliosheath, the heliopause, and the interstellar medium. We are going to explore the shocking discoveries Voyager made as it crossed each of these boundaries, the things that confirmed our theories and the things that shattered them. We are going to talk about the mysterious magnetic highway that no one predicted, the plasma density puzzle that still has scientists scratching their heads, the temperature anomaly that defies our models, and that eerie, persistent hum in the void between the stars. We are going to talk about what all of this means for us here on Earth, how the heliosphere protects us from deadly galactic cosmic rays, how changes in the heliosphere could affect our planet's climate and even the evolution of life, how Voyager's data is helping us understand whether planets around other stars might be habitable. And we are going to look to the future at where Voyager is going, how long it will last, and what will happen when it finally goes silent. This is going to be the most comprehensive, most detailed, most in-depth exploration of the Voyager mission you have ever seen. We are covering every angle, every discovery, every mystery. If you are someone who looks up at the night sky and feels that pull, that deep primal curiosity about what lies beyond the familiar, then you are in exactly the right place. This channel is dedicated to exploring the deepest, most fascinating mysteries of the universe, And today, we are going further than we have ever gone before. If you are ready for this journey, hit that subscribe button right now. Smash the like button so that more people can discover this story. And drop a comment telling me this. How far do you think the solar system extends? Give me a number, give me a guess, give me your wildest theory. I will pin the most interesting answer. Now, let us go back to the very beginning. Let us go back to the 1970s, to a time when humanity looked up at the planets and decided to do something audacious, something bold, something that would echo across the centuries. To understand why Voyager exists, you need to understand something about the planets in our solar system and the way they dance around the sun. The planets do not just orbit the sun in simple circles. They move at different speeds, at different distances, in orbits that are slightly elliptical, and as a result, their positions relative to each other are constantly changing. Most of the time, the outer planets, Jupiter, Saturn, Uranus, and Neptune, are scattered around the solar system in no particular useful arrangement. But very, very rarely, they line up in a configuration that creates an extraordinary opportunity. In the late 1970s, something remarkable was about to happen. Jupiter, Saturn, Uranus, and Neptune were going to be arranged in a sweeping arc on the same side of the Sun, in a configuration that would allow a single spacecraft to visit all four of them, one after another, using the gravity of each planet to slingshot to the next. This alignment happens once every 176 years. Let that sink in. The last time this alignment occurred, Napoleon was still alive. The United States was a young nation. The Industrial Revolution was just beginning. And the next time it will happen, it will be the 2150s. Every human being alive today will be long dead. A young aerospace engineer at NASA's Jet Propulsion Laboratory named Gary Flandreau recognized this opportunity in 1964. He calculated that a spacecraft launched in the late 1970s could use what is called gravitational assist, a technique where a spacecraft flies close to a planet and uses that planet's gravity to gain speed and change direction, to visit all four giant planets in a single mission. The idea was breathtaking in its elegance. Instead of needing enough fuel to fly directly to each planet, which would require a rocket far larger than anything that existed, the spacecraft could essentially borrow energy from the planets themselves. Each flyby would accelerate the spacecraft and bend its trajectory toward the next target. It was like a cosmic billiard shot, using the gravity wells of the giant planets as bumpers. Flandreau called this concept the Grand Tour, and it captured the imagination of scientists and engineers across the country. NASA initially embraced the Grand Tour concept with enthusiasm. They began planning an ambitious program that would send multiple sophisticated spacecraft on different trajectories through the outer solar system. The original Grand Tour program envisioned large, complex, expensive spacecraft equipped with cutting-edge instruments. But then reality intruded, as it so often does. The early 1970s were a difficult time for NASA. The Apollo program was winding down. Public interest in space was declining. The Vietnam War was draining the national budget, and Congress, facing competing priorities and a growing sense that space exploration was an expensive luxury, began slashing NASA's budget with enthusiasm. The Grand Tour program, with its hefty price tag, was one of the casualties. Congress killed the Grand Tour. The dream of sending spacecraft to all four outer planets seemed dead, but the scientists and engineers at the Jet Propulsion Laboratory were not ready to give up. They came up with a clever strategy, a bit of bureaucratic judo that would save the mission. Instead of the ambitious Grand Tour, they proposed a much more modest mission called Mariner Jupiter-Saturn. The name was deliberately unambitious. It was just a Mariner-class mission, part of an existing, well-understood program of interplanetary probes, and it was only going to Jupiter and Saturn. Nothing fancy, nothing expensive. Congress approved it. But here's the thing. The engineers at JPL designed the spacecraft to be far more capable than a simple Jupiter-Saturn mission required. They built in redundancy, durability, and flexibility. They equipped the spacecraft with instruments that could, if everything went well, continue operating for years beyond the primary mission. And they designed the trajectory so that, after completing the Saturn encounter, the spacecraft could, if NASA chose to extend the mission, continue on to Uranus and Neptune. The plan was simple. Promise Jupiter and Saturn, but build for the grand tour. Deliver on the promise first, and then ask for more. It was a calculated gamble, and it worked brilliantly. 2 spacecraft were built, Voyager 1 and Voyager 2. And here is a fun little quirk of history that most people get wrong. Voyager 2 was launched first on August 20th, 1977. Voyager 1 was launched 16 days later on September 5th, 1977. Despite its later launch, Voyager 1 was placed on a faster trajectory that would get it to Jupiter and Saturn first. The names referred not to their launch order, but to the order in which they would arrive at their first target. Voyager 1 would arrive at Jupiter before Voyager 2, hence the name. It is a small detail, but it illustrates the meticulous planning that went into every aspect of this mission. Let us talk about what these spacecraft actually were, because understanding the engineering is crucial to appreciating the magnitude of what they achieved. Each Voyager spacecraft weighed approximately 825 kilograms. They were built around a 10-sided bus, a central structure that housed the electronics and computers. Extending from this bus was a large, white, high-gain antenna, 3.7 meters in diameter, which was used to communicate with Earth. This antenna always had to be pointed precisely at Earth, because the radio beam it produced was narrow and focused. Even a slight misalignment would mean losing contact. For power, the Voyagers used 3 radioisotope thermoelectric generators, or RTGs. This is one of those engineering choices that sounds simple but is actually profound. Solar panels, which work fine for spacecraft near the Sun, are useless in the outer solar system. At Jupiter's distance, sunlight is only about 4% as intense as at Earth. At Neptune, it is less than 1/10 of 1%. You would need solar panels the size of football fields to generate useful power, and they would need to be pointed at the Sun with extreme precision. So instead, the Voyagers carry small cylinders of plutonium-238, a radioactive isotope that generates heat as it decays. Thermocouples convert this heat directly into electricity. It is reliable, it requires no moving parts, and it works regardless of distance from the Sun. At launch, each spacecraft's RTGs produced about 470 watts of electricity, roughly enough to power a few household light bulbs. And here is the critical detail that will matter enormously later in our story. The plutonium-238 in the RTGs decays over time, losing about 4 watts of power per year. This means the Voyagers have been slowly, inexorably losing power for over 4 decades. This ticking clock has shaped every decision about the mission for the last 20 years, and will ultimately determine when the Voyagers fall silent. The scientific instrument package on each Voyager was remarkable for its time. Each spacecraft carried 11 scientific instruments, including 2 television cameras for imaging, an infrared spectrometer for measuring temperatures and compositions, an ultraviolet spectrometer for studying atmospheric chemistry, a magnetometer for measuring magnetic fields mounted on a long boom to keep it away from the spacecraft's own magnetic interference, a plasma science instrument for measuring the solar wind, a cosmic ray detector for measuring high-energy particles, a low-energy charged particle detector, a planetary radio astronomy receiver, a photopolarimeter, and a plasma wave instrument. That last one, the plasma wave instrument, would turn out to be crucial decades later, when Voyager reached the edge of the solar system and used it to detect vibrations in the interstellar plasma, the key evidence that finally confirmed the crossing into interstellar space. The onboard computers were, by modern standards, hilariously primitive. Each Voyager had 3 computers: the computer command subsystem, the flight data subsystem, and the attitude and articulation control subsystem. Together, they had about 69.63 kilobytes of memory. To put this in perspective, the text of this video script alone would overwhelm Voyager's entire computer memory several times over. A single photo from your smartphone contains more data than Voyager's computer can hold. And yet, these computers have been running continuously, without a reboot, without a hardware replacement, without any physical maintenance whatsoever, for almost 5 decades. They have executed billions of commands, processed countless scientific measurements, and navigated the spacecraft through the most complex series of planetary encounters ever attempted. They are, without question, among the most reliable computers ever built. The communication system deserves special attention because it illustrates one of the most remarkable aspects of the entire mission. Voyager's radio transmitter operates at just 23 watts. 23 watts. That is less power than a typical refrigerator light bulb. And with that 23 watts, from a distance of billions of kilometers, Voyager sends its data back to Earth. How is this possible? The answer lies on both ends of the link. The spacecraft's high-gain antenna focuses the radio signal into a tight beam pointed at Earth. And on Earth, NASA's Deep Space Network, a collection of enormous radio antennas scattered around the globe in California, Spain, and Australia, uses dishes up to 70 meters in diameter to catch those incredibly faint signals. The signal that arrives at Earth from Voyager is so weak that the total power received is measured in fractions of a femtowatt, a unit so small that it defies everyday comprehension. It is roughly 20 billion times weaker than the power of a digital watch battery. And yet engineers can extract meaningful scientific data from this whisper across the cosmos. It is one of the quiet miracles of modern engineering. And then there is the golden record. This is where the Voyager story transcends engineering and science, and enters the realm of art, philosophy, and the deepest questions about what it means to be human. The golden record was the brainchild of a committee chaired by Carl Sagan, the astronomer, author, and science communicator who was arguably the most famous scientist in America at the time. Sagan assembled a small team that included the writer Anne Druyan, who would later become his wife, the artist John Lomborg, and several scientists and musicians. Their task was extraordinary: create a message that could be understood by an alien civilization that knows nothing about Earth, nothing about humanity, nothing about our biology or our culture or our history. A message that might not be found for millions or even billions of years. The result was a 12-inch gold-plated copper phonograph record, enclosed in a protective aluminum jacket, with a cartridge and stylus for playback. The cover of the record was engraved with symbolic instructions showing how to play the record, the speed at which it should rotate, how to decode the images, and even a pulsar map showing the position of the sun relative to 14 pulsars, so that an alien civilization could determine where and when the record came from. Inside, the record contained 115 images encoded as analog signals, including photographs of Earth, its continents and oceans, its plants and animals, its people and cities, diagrams of human anatomy and DNA, mathematical and scientific diagrams, and images of the solar system. There were greetings in 55 languages, from ancient Sumerian to modern Mandarin, from formal United Nations declarations to a simple "Hello" from the children of planet Earth. There was a 90-minute selection of music chosen to represent the incredible diversity of human musical expression, from Bach's Brandenburg Concerto to Beethoven's Fifth Symphony, from Chuck Berry's Johnny B. Good to traditional music from Peru, Azerbaijan, Japan, India, and dozens of other cultures. And there were the sounds of Earth: volcanoes, earthquakes, thunder, wind, rain, surf, birdsong, whale songs, the sounds of crickets and frogs, the bark of a dog, the footsteps of a human, a heartbeat, laughter, and the sound of a kiss. Anne Druyan later described a remarkable moment during the recording process. She was hooked up to a device that recorded her brainwaves and other physiological signals, attempting to capture the electrical patterns of human thought and emotion. During the recording session, she meditated on a wide range of subjects: the history of Earth, the evolution of life, the problems of the world, her hopes for the future. What she did not reveal until later was that during that session, she and Carl Sagan had just fallen in love, and her brainwaves during the recording were, in part, the electrical signature of that love. So somewhere on the golden record, encoded in the oscillations of a brain scan, is the neural imprint of a woman falling in love. And that message is now traveling through interstellar space, a love letter written in brainwaves, carried on a spacecraft that will outlast the sun. The probability of anyone ever finding the golden record is, by any rational calculation, essentially zero. The spacecraft are heading into the vast emptiness between the stars, where the distances are so enormous and the probability of a chance encounter is so infinitesimally small that the record will almost certainly drift forever without being found. Carl Sagan knew this. Everyone on the team knew this. They created the record anyway, because the golden record was never really for the aliens. It was for us. It was a mirror held up to humanity, a way of saying, this is who we are, this is what we value, this is what we sound like when we are at our best. It was an act of breathtaking optimism in a world racked by Cold War tensions, nuclear fears, and environmental anxieties. It said, simply and eloquently, we are here, we are curious, we are hopeful, and we are reaching out. With all of this context, with all of this engineering and philosophy and ambition loaded onto two small spacecraft, Voyager 1 and Voyager 2 left Earth in the summer of 1977 and began their journey toward the outer planets. And what they found there would change everything. Voyager 1 reached Jupiter in March 1979, with Voyager 2 following in July of the same year. Jupiter was already the most studied planet in the solar system after Earth. Astronomers had been observing it through telescopes for centuries. They knew about the Great Red Spot, the enormous storm in Jupiter's atmosphere that has been raging for at least 350 years and is large enough to swallow Earth 2 or 3 times over. They knew about Jupiter's immense size, its powerful magnetic field, and its system of moons. But they had never seen Jupiter up close. They had never resolved the fine details of its atmosphere, its rings or its moons. Voyager was about to change all of that. The Jupiter encounter was, in many ways, the moment when Voyager justified its entire existence. The spacecraft returned thousands of images of Jupiter, revealing the planet's atmosphere in stunning detail. The Great Red Spot turned out to be even more complex than anyone had imagined. A swirling vortex of counter-rotating storms within storms, with wind speeds exceeding 600 kilometers per hour. The atmospheric bands that give Jupiter its distinctive striped appearance were revealed to be incredibly dynamic, with eddies, turbulence, and interactions between bands that created complex, beautiful patterns. Jupiter's clouds were not simple layers, but a three-dimensional tapestry of ammonia ice, ammonium hydrosulfide, and water clouds at different altitudes, colored by trace compounds that scientists are still working to identify. But the real surprises came from Jupiter's moons. Jupiter has a vast system of satellites, and the four largest, Io, Europa, Ganymede, and Callisto, known as the Galilean moons because Galileo discovered them in 1610, were particular targets of interest. What Voyager found at these moons was nothing short of revolutionary. Let us start with Io, because what happened there is one of the most dramatic discovery stories in the history of planetary science. Before Voyager arrived, most scientists expected Io to be a dead, cratered world, much like our own moon. It was a small body, only slightly larger than Earth's moon, and the prevailing wisdom was that small bodies cool quickly and become geologically dead early in their history. The assumption was reasonable, but it was spectacularly wrong. A young JPL engineer named Linda Morabito was processing navigation images of Io, images that were taken not for scientific purposes, but to help determine Voyager's exact trajectory by comparing the observed position of Io against its predicted position. In one of these images, she noticed something peculiar. A strange, crescent-shaped feature on the limb of Io, extending above the surface. At first, she wondered if it might be another moon behind Io, but after careful analysis, she realized what she was looking at. It was a volcanic eruption, an enormous volcanic plume rising 300 kilometers above the surface of Io, shooting material into space at speeds of over 1 kilometer per second. Io was not dead. It was the most volcanically active body in the entire solar system. This discovery sent shockwaves through the scientific community. How could such a small moon be so geologically active? The answer, it turned out, had been predicted just weeks before Voyager's arrival by 3 scientists, Stan Peele, Patrick Casson, and Ray Reynolds, who published a paper arguing that tidal forces from Jupiter should heat Io's interior enough to cause widespread volcanism. Their prediction was brilliantly confirmed by Voyager's observations. Here is how it works. Io orbits Jupiter in a slight ellipse, and its orbit is locked into a resonance with the orbits of Europa and Ganymede. This means the gravitational pulls from these other moons prevent Io's orbit from becoming perfectly circular. As Io moves closer to and farther from Jupiter in each orbit, the massive gravitational field of the giant planet squeezes and stretches Io, flexing its interior and generating enormous amounts of frictional heat. Imagine squeezing a rubber ball rapidly in your hand. The ball gets warm. Now imagine that the ball is the size of a world, and the hand doing the squeezing is the gravity of the largest planet in the solar system. The amount of heat generated is staggering, enough to keep Io's interior molten and to drive volcanic eruptions that continuously resurface the entire moon. Io has no impact craters because its surface is so young, constantly being covered by fresh volcanic deposits. The entire surface is painted in vivid yellows, oranges, reds, blacks, and whites, the colors of various sulfur compounds and silicate lavas. Voyager discovered at least 9 active volcanic eruptions on Io during its flybys, along with hundreds of volcanic calderas, lava flows extending hundreds of kilometers, and volcanic plumes shooting material to astonishing heights. Some of the eruptions were so powerful that they ejected material completely out of Io's gravitational field, creating a torus of ionized particles that orbits Jupiter and interacts with its magnetic field in complex ways. The discovery of Io's volcanism was a profound moment in planetary science because it demonstrated that geological activity is not just about a body's size or age, but about its gravitational environment. It opened up entirely new ways of thinking about what makes a world alive. Then there was Europa. If Io was the solar system's most dramatic surprise, Europa was its most tantalizing. Voyager's images revealed a world utterly unlike anything scientists had seen before. Europa's surface was smooth, smoother than almost any other solid body in the solar system. It was covered in water ice, and that ice was crisscrossed by an intricate network of dark lines, like the veins on a bloodshot eye, stretching across the surface in complex, intersecting patterns. There were very few impact craters, which meant the surface was young, constantly being refreshed by some geological process. And the smoothness of the surface, combined with the pattern of cracks, strongly suggested something extraordinary. Beneath Europa's icy shell, there was liquid water, an ocean, a global ocean of salt water, kept liquid by the same tidal heating that drives Io's volcanism, but acting more gently on Europa due to its greater distance from Jupiter. The implications were staggering. On Earth, wherever we find liquid water, we find life. From the boiling hot springs of Yellowstone to the lightless depths of the ocean floor, from the frozen lakes beneath Antarctic glaciers to the microscopic films of water inside rocks deep in the Earth's crust, life finds a way. If Europa has a global ocean of liquid water, warmed from below by tidal heating, with a rocky seafloor where water and rock interact, then Europa has many of the ingredients that life needs. Voyager could not confirm the ocean's existence. That would come later with the Galileo mission, but the tantalizing clues it provided launched a scientific obsession with Europa that continues to this day. As of now, NASA and the European Space Agency are building missions specifically designed to investigate Europa's ocean and search for signs of life. All of that traces back to what Voyager glimpsed in 1979. Ganymede, the largest moon in the solar system, larger even than the planet Mercury, revealed a surface of two distinct types: older, darker, heavily cratered terrain, and younger, lighter, grooved terrain with complex tectonic features. Voyager's images showed that Ganymede had experienced significant geological activity in its past, with its surface being deformed and resurfaced by internal processes. Callisto, the outermost of the 4 Galilean moons, was the expected dead, cratered world, its surface so ancient and heavily bombarded that it resembles the lunar highlands, a record of the violent early history of the solar system preserved in ice and rock. The contrast between the 4 Galilean moons, from the volcanic fury of Io to the frozen antiquity of Callisto, with the tantalizing oceans of Europa and the tectonic complexity of Ganymede in between, demonstrated that the Jupiter system was not just a planet with some moons. It was a miniature solar system in its own right, with a diversity of worlds that rivaled anything found orbiting the Sun. Jupiter also delivered a surprise in the form of a ring system. Before Voyager, rings were known only around Saturn. Voyager discovered that Jupiter also has a ring system, though a faint and tenuous one compared to Saturn's magnificent display. Jupiter's rings are composed primarily of small dust particles, knocked off the surfaces of the small inner moons by micrometeorite impacts. The discovery of Jupiter's rings was important not just for what it revealed about Jupiter, but for what it suggested about planetary ring systems in general. They might be common features of giant planets, not unique to Saturn. This prediction was later confirmed when Voyager discovered rings around Uranus and Neptune as well. The radiation environment near Jupiter was one of the most hazardous aspects of the encounter. Jupiter has the most powerful magnetic field of any planet in the solar system, roughly 20,000 times stronger than Earth's. This magnetic field traps charged particles from the solar wind and from Io's volcanic emissions, creating intense radiation belts that make the worst radiation environments on Earth look benign. As Voyager passed through these radiation belts, its electronics were bombarded with high-energy particles. Some instruments experienced anomalies, some data was corrupted, and the spacecraft accumulated a significant radiation dose. The fact that both Voyagers survived the Jupiter encounter and continued functioning was a testament to the robustness of their design. After Jupiter, the next target was Saturn. Voyager 1 arrived at Saturn in November 1980, with the Voyager 2 following in August 1981. Saturn, the jewel of the solar system, the planet whose rings have captivated human observers since Galileo first glimpsed them and mistakenly thought they were ears or adjacent companion bodies, was about to reveal its secrets in unprecedented detail. Voyager's images of Saturn's ring system were breathtaking. From a distance, Saturn's rings appear as a few broad, smooth bands of material. But up close, Voyager revealed that the rings are made up of thousands upon thousands of individual ringlets, a level of complexity that no one had anticipated. Each ringlet is composed of countless particles of ice and rock, ranging in size from tiny grains of dust to chunks as large as houses, all orbiting Saturn in incredibly thin, flat paths. The rings are extraordinarily thin relative to their width. If you scaled Saturn's rings down so that their diameter was a kilometer, they would be thinner than a sheet of paper. And within this impossibly thin sheet, Voyager found structures that defied explanation. There were the spokes in the B ring, dark, radial features that appeared to float above the ring plane, rotating with the planet rather than orbiting at the correct Keplerian speed for their distance from Saturn. They seemed to defy the laws of orbital mechanics, and their origin was debated for decades. The leading theory involves tiny dust particles being levitated above the ring plane by electrostatic forces, charged by lightning in Saturn's atmosphere or by impacts of high-energy electrons from the magnetosphere. But even now, the spoke phenomenon is not fully understood. There was the F ring, a narrow dynamic ring just outside the main ring system, which Voyager revealed to be braided, kinked, and clumped in ways that seemed physically impossible. The F ring is shepherded by two tiny moons, Prometheus and Pandora, which orbit just inside and just outside the ring, and their gravitational influence creates the ring's bizarre, ever-changing structure. These shepherd moons were a Voyager discovery, and they introduced the concept of gravitational shepherding, the idea that small moons can confine and shape ring material, a concept that has since been found to operate throughout Saturn's ring system and beyond. Voyager also resolved the Cassini division, the most prominent gap in Saturn's rings, visible even through small telescopes on Earth. The Cassini division turned out not to be truly empty, but to contain its own set of ringlets, much fainter than the main rings but definitely present. The gap is maintained primarily by a gravitational resonance with the moon Mimas. Particles in the Cassini division orbit Saturn in exactly half the time it takes Mimas to complete one orbit, and the repeated gravitational tugs from Mimas at the same point in each orbit clear the gap over time. This is another example of orbital resonance shaping the structure of the solar system, the same basic phenomenon that heats Io's interior and creates the Kirkwood gaps in the asteroid belt. But the single most consequential event of the Saturn encounter was not about the rings or the planet itself. It was about Titan. Titan is Saturn's largest moon, and it had been a source of fascination and mystery since the astronomer Gerard Kuiper detected an atmosphere around it in 1944. Titan is the only moon in the solar system with a substantial atmosphere, and pre-Voyager observations had suggested that this atmosphere might be rich in nitrogen and organic compounds. Some scientists speculated that Titan's surface conditions might resemble those of early Earth, before life began. making it a kind of prebiotic chemistry laboratory frozen in time. Voyager 1's trajectory at Saturn was designed to bring it close to Titan for a detailed study. But this close approach came with a profound cost. The trajectory required to fly close to Titan would bend Voyager 1's path sharply upward, out of the plane in which the planets orbit. After the Titan flyby, Voyager 1 would be heading up and out of the solar system, unable to visit Uranus or Neptune. This was one of the most agonizing decisions in the mission's history. The Grand Tour, the dream of visiting all 4 outer planets with a single spacecraft, would be sacrificed for a close look at Titan. Scientists debated fiercely, but ultimately the scientific potential of Titan won out. The thinking was pragmatic. Voyager 2 was on its way and could continue to Uranus and Neptune if Voyager 1 could not. But if the Titan flyby was skipped, there was no other opportunity to study this unique world up close. The decision was made. Voyager 1 would fly close to Titan. Voyager 2 would carry the Grand Tour torch. Voyager 1's Titan flyby was both a triumph and a disappointment, in ways that proved to be scientifically profound. The triumph was the wealth of data about Titan's atmosphere. Voyager confirmed that Titan's atmosphere is primarily nitrogen, much like Earth's, but about 50% denser, with a surface pressure about 1.5 times that of Earth. The atmosphere contains significant amounts of methane, ethane, and a zoo of complex organic molecules, hydrocarbons, and nitrogenous compounds formed by the action of solar ultraviolet light on nitrogen and methane. The atmospheric chemistry of Titan was revealed to be astonishingly complex, a natural laboratory for prebiotic chemistry operating on a planetary scale. The disappointment was that Voyager could not see Titan's surface. The thick, orange, smoggy haze of organic compounds in Titan's upper atmosphere was completely opaque to Voyager's cameras. Instead of revealing the surface of this tantalizing world, Voyager saw only an unbroken orange sphere. What lay beneath the haze, whether there were lakes, oceans, mountains, or plains, remained a mystery that would not be solved until the Cassini-Huygens mission arrived at Saturn in 2004 and dropped a probe through Titan's atmosphere to the surface, revealing a world of methane lakes, ethane rivers, and ice rock mountains shrouded in perpetual orange twilight. But it was Voyager that first characterized Titan's atmosphere and ignited the scientific curiosity that drove those later missions. After the Titan flyby, Voyager 1 arced upward and out of the ecliptic plane, heading toward interstellar space. Its planetary mission was over. But as we will see, its greatest discoveries were still decades in the future. Meanwhile, Voyager 2 sailed on toward Saturn, and after its own Saturn encounter in August 1981, it continued on the path that Voyager 1 had been forced to abandon. Voyager 2 was now humanity's Grand Tour spacecraft, the only machine in history that would visit all 4 outer planets. Before we continue with Voyager 2's journey, there's a moment in the Voyager story that we need to pause and appreciate. A moment that has nothing to do with scientific instruments or engineering feats. A moment of pure philosophical revelation that has resonated across human culture for decades. On February 14, 1990, at the urging of Carl Sagan, NASA commanded Voyager 1 to turn its cameras around and take one final series of photographs. Not of a planet or a moon or any specific scientific target, but of the solar system itself, from the outside looking back. The result was a series of images known as the Family Portrait, showing 6 of the 9 planets, as they were counted then, as tiny points of light against the blackness of space. One of these images captured Earth. Our planet appeared as a tiny, pale, blue-white dot, occupying less than a single pixel, suspended in a band of scattered sunlight that happened to fall across the camera's field of view. From Voyager's vantage point 6 billion kilometers away, Earth was almost invisible, a mote of dust in a sunbeam. Carl Sagan looked at this image and wrote one of the most profound passages in the history of science literature. He wrote about how that tiny dot was home to everyone we have ever known, every human being who has ever lived, every king and peasant, every young couple in love, every mother and father, every hopeful child, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. He wrote about the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. He wrote about how our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this pale point of light. And he concluded that there is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world, and that it underscores our responsibility to deal more kindly with one another, and to preserve and cherish the pale blue dot, the only home we have ever known. After the pale blue dot image was taken, Voyager 1's cameras were turned off permanently. They would never be used again. The power they consumed was needed for other instruments that would be critical when Voyager reached the edge of the solar system. The cameras had done their job. They had shown us our cosmic neighborhood in ways we had never seen before. Now, it was time for the other instruments to take the lead. Voyager 2 continued its grand tour. On January 24, 1986, it arrived at Uranus, becoming the first and, as of now, the only spacecraft ever to visit this peculiar world. Think about that for a moment. In the entire history of human space exploration, with all our technology and ambition and capability, only one spacecraft has ever visited Uranus. And it happened almost 40 years ago. Everything we know about Uranus from close-up observation comes from a single flyby by Voyager 2. Uranus is the solar system's most eccentric planet, literally. It orbits the Sun tilted on its side, with an axial tilt of 97.77 degrees. While other planets spin like tops as they orbit the Sun, Uranus rolls along its orbit like a ball. The most widely accepted explanation for this bizarre orientation is that early in the solar system's history, a massive object, perhaps an Earth-sized protoplanet, collided with Uranus and knocked it onto its side. The consequences of this extreme tilt are profound. Instead of having traditional seasons caused by a modest axial tilt like Earth's 23 degrees, Uranus experiences extreme seasons in which each pole alternately points directly at the Sun and directly away from it. At the solstices, one pole experiences continuous sunlight, while the other is plunged into decades of darkness. At the time of Voyager's flyby, the South Pole was pointed almost directly at the Sun, meaning Voyager was essentially looking down at a pole rather than at an equator, which made mapping the planet's atmospheric features more challenging. Voyager found Uranus to be a surprisingly bland-looking world compared to Jupiter and Saturn. Its atmosphere appeared almost featureless, a uniform blue-green color caused by methane in the upper atmosphere absorbing red light. Where Jupiter and Saturn had displayed dramatic bands, storms, and eddies, Uranus seemed quiet and calm. Later, observations by the Hubble Space Telescope and ground-based observatories would reveal that Uranus does have atmospheric features, including clouds, bands, and even storms, but they are subtle and were difficult for Voyager to detect during its brief flyby. Uranus's magnetic field was one of the encounter's biggest surprises. On Earth, Jupiter, and Saturn, the magnetic field is roughly aligned with the planet's rotation axis. The magnetic poles are near the rotational poles, On Uranus, the magnetic field is tilted by a whopping 59 degrees relative to the rotation axis, and is offset from the center of the planet by about a third of the planet's radius. This means the magnetic field is both tilted and shifted, creating a highly asymmetric magnetosphere that wobbles dramatically as the planet rotates. Scientists had expected Uranus's magnetic field to be unusual, given its extreme axial tilt, but the degree of misalignment was far greater than predicted. The discovery suggested that the magnetic field is generated not in the planet's core, as on Earth and Jupiter, but in a shell of electrically conducting fluid, possibly a mixture of water, ammonia, and methane under extreme pressure at intermediate depths within the planet. Voyager discovered 10 new moons of Uranus, bringing the total known at the time to 15. But the most fascinating moon was Miranda, the smallest and innermost of the 5 major moons. Miranda's surface was a geological jigsaw puzzle, a patchwork of wildly different terrain types crammed together in seemingly random fashion. There were old, heavily cratered plains right next to young, smooth, grooved terrain. There were enormous geological features called coronae, roughly oval regions of concentric ridges and grooves that looked like racetracks or the growth rings of a tree. And there was Verona Rupes, a cliff face roughly 20 kilometers high, the tallest known cliff in the solar system. If you stood at the edge and dropped a rock, it would take about 12 minutes to hit the bottom, because Miranda's gravity is so weak. Miranda looked like it had been shattered and reassembled, and that was, in fact, one early theory, that a massive impact had broken Miranda into pieces, which then gravitationally reaccreted in a random jumble. More recent analysis suggests that the bizarre surface is more likely the result of tidal heating and internal geological processes, perhaps similar in principle to what drives activity on Io and Europa, but acting on a much smaller body. 3 years later, on August 25, 1989, exactly 12 years after launch, Voyager 2 reached Neptune, the final planetary encounter of the Grand Tour. Neptune was the most distant planet visited by any spacecraft, and it was one of the least studied objects in the solar system. From Earth, Neptune appears as a tiny, faint blue dot, barely resolvable even with the largest telescopes. Voyager 2 was about to see it up close for the first, and so far the only, time. Neptune was anything but boring. Where Uranus had appeared calm and featureless, Neptune was dynamic, dramatic, and wild. Voyager discovered the Great Dark Spot, a massive storm system in Neptune's southern hemisphere, similar in some ways to Jupiter's Great Red Spot, but even more dynamic and ephemeral. When Hubble observed Neptune a few years later, the Great Dark Spot had vanished, though new spots had appeared elsewhere. Neptune's atmosphere displayed vivid cloud features, including high-altitude methane ice clouds that cast shadows on the cloud deck below, allowing scientists to measure their altitude. And Neptune's winds were the fastest ever measured in the solar system, reaching speeds of up to 2,100 kilometers per hour. This was deeply puzzling. Neptune receives very little heat from the sun, only about 1,000th the amount Earth receives, yet it has the most violent atmospheric dynamics of any planet. The energy driving these extreme winds must come primarily from the planet's internal heat, and the mechanism by which this internal heat generates such fierce winds in such a cold, distant atmosphere remains one of the great unsolved problems in planetary science. Neptune's magnetic field turned out to be just as weird as Uranus's, tilted 47 degrees from the rotation axis and offset from the planet's center. This was a crucial finding because it showed that the bizarre magnetic field geometry of Uranus was not just a quirk of that one planet, but might be a common feature of ice giant planets. Since ice giants may be among the most common types of planets in the galaxy, based on exoplanet surveys, Understanding their magnetic fields is important for understanding planetary magnetism across the cosmos. Voyager discovered 6 new moons of Neptune and confirmed the existence of the planet's ring system, which had been suspected from ground-based observations but never clearly imaged. The rings were faint and clumpy, with denser concentrations of material in some segments that had made them difficult to detect from Earth. But the single most remarkable discovery at Neptune was Triton, Neptune's largest moon. Triton is one of the most extraordinary objects in the solar system, and Voyager's flyby revealed it to be a world that breaks all the rules. Triton orbits Neptune backwards, while virtually every other large moon in the solar system orbits its parent planet in the same direction that the planet rotates, prograde. Triton orbits in the opposite direction, retrograde. This is an extremely strong indicator that Triton did not form alongside Neptune but was captured from an independent orbit around the Sun. The most likely scenario is that Triton originated in the Kuiper Belt, the vast population of icy bodies beyond Neptune, and was captured by Neptune's gravity during a close encounter, probably through a collision or three-body interaction that drained enough of Triton's kinetic energy for it to become trapped in Neptune's gravitational well. The consequences of this capture are profound. When Triton was first captured, it would have been in a highly elliptical orbit, and the tidal forces from Neptune would have flexed and heated its interior enormously as its orbit gradually circularized over millions of years. This intense tidal heating would have kept Triton's interior warm for a long time, and may be responsible for the geological features Voyager observed. And what Voyager observed on Triton was astonishing. The surface temperature was just 38 Kelvin, minus 235 degrees Celsius, making it one of the coldest surfaces in the solar system. Despite this extreme cold, Triton showed unmistakable signs of geological activity. There were vast, smooth plains of nitrogen ice. There were a rugged, cantaloupe-textured terrain unlike anything seen anywhere else. And most remarkably, Voyager spotted active geysers, plumes of nitrogen gas and dark material erupting from beneath the surface to heights of about 8 kilometers before being blown downwind by Triton's thin atmosphere. These were not volcanic eruptions in the traditional sense, but a form of cryovolcanism, where the lava is not molten rock but volatile ices. Nitrogen, in this case, heated by sunlight penetrating the transparent nitrogen ice and warming the darker material beneath, creating pockets of pressurized gas that eventually erupt through the surface. Active geological processes on a world where temperatures never rise above minus 200 degrees. The solar system never ceases to amaze. Triton's fate is sealed. Because it orbits retrograde, tidal interactions are gradually draining energy from its orbit, causing it to spiral slowly inward toward Neptune. In a few billion years, Triton will cross Neptune's Roche limit, the distance at which tidal forces will tear a body apart, and will be shredded into a spectacular ring system that may rival or even surpass Saturn's. If any astronomers exist in the solar system billions of years from now, they will witness the creation of a magnificent new ring system. But that is a story for the very distant future. The Neptune encounter marked the end of Voyager 2's planetary mission and the end of the Grand Tour. In 12 years, the 2 Voyager spacecraft had transformed our understanding of the outer solar system. They had discovered active volcanoes on Io, hints of an ocean on Europa, the complex structure of Saturn's rings, the bizarre magnetic fields of Uranus and Neptune, the dynamic atmosphere of Neptune, and the captured geyser-blowing world of Triton. They had discovered new moons, new rings, and new phenomena. They had revolutionized planetary science and inspired a generation of scientists, engineers, and dreamers. But the grand tour was only the beginning. After Neptune, both the Voyagers were redirected for a new phase of the mission, the Voyager Interstellar mission. Their planetary cameras were turned off to save power. Most of their planet-focused instruments were shut down. The instruments that remained active were those that could study the space environment itself: the magnetometer, the cosmic ray detector, the charged particle instruments, and the plasma wave instrument. These instruments would become the eyes and ears of humanity's first voyage to the edge of the solar system. And here is where we need to stop and think carefully about what the edge of the solar system actually means, because it turns out to be a far more complex and interesting question than most people realize. When most people think about the edge of the solar system, they imagine a boundary, a line or a wall where the solar system ends and interstellar space begins. But there is no single, clean boundary. There are actually several different definitions of where the solar system ends, depending on what criterion you use, and they correspond to vastly different distances from the Sun. The first and most intuitive definition is the orbital edge, the distance of the most distant objects that orbit the Sun. By this definition, the solar system extends at least to the Kuiper belt, the region beyond Neptune where Pluto and thousands of other icy bodies orbit, and, arguably much farther, to the Oort cloud, a hypothetical, but strongly supported by indirect evidence, shell of trillions of icy bodies extending from roughly 2,000 astronomical units to perhaps 100,000 astronomical units from the Sun. An astronomical unit, or AU, is the average distance from the Earth to the Sun, about 150 million kilometers. So the Oort cloud, if it exists as theorized, extends from about 300 billion kilometers to 15 trillion kilometers from the Sun. By this definition, the solar system is enormous, and Voyager, despite having traveled for decades, has barely scratched the surface. Voyager 1 is currently at roughly 165 astronomical units from the Sun. The inner edge of the Oort cloud is at roughly 2,000 astronomical units. Voyager has a very, very long way to go. But there's another definition of the edge that is, in many ways, more physically meaningful. This is the heliospheric edge, the boundary of the heliosphere. The heliosphere is the vast bubble of charged particles and magnetic field that the Sun creates around itself. To understand the heliosphere, you need to understand the solar wind. The Sun is not just a ball of hot gas sitting passively in space. It is actively blowing material outward in all directions. The solar corona, the outermost layer of the Sun's atmosphere, is so hot, millions of degrees, that it cannot be held in by the Sun's gravity. Instead, it streams outward into space as a continuous flow of charged particles, mostly protons and electrons, moving at speeds of roughly 400 to 750 kilometers per second. This is the solar wind. It carries with it the Sun's magnetic field, dragging it outward and stretching it into a vast, spiraling pattern that fills the solar system. The solar wind creates a bubble around the Sun. Inside this bubble, the environment is dominated by the Sun's particles and magnetic field. Outside this bubble is the interstellar medium, the very thin gas and dust that fills the space between the stars, which has its own particles, its own magnetic field, and its own dynamics. The boundary between the Sun's domain and the interstellar medium is the edge of the heliosphere, and it is this boundary that the Voyager spacecraft were the first human-made objects to approach, study, and cross. The structure of this boundary is not simple. It is not a sharp wall. It is a series of regions, each with different physical characteristics, and understanding these regions is essential to understanding what Voyager detected. The first boundary is the termination shock. As the solar wind streams outward from the Sun, it is moving at supersonic speeds, faster than the speed of sound in the solar wind plasma. When this supersonic flow encounters the back pressure of the interstellar medium, it abruptly slows down to subsonic speeds. This sudden deceleration creates a shock wave, much like the sonic boom created by a supersonic aircraft, but in reverse. At the termination shock, the solar wind slows from roughly 400 kilometers per second to about 100 kilometers per second or less. The kinetic energy of the fast-moving solar wind is converted into heat, causing the temperature of the solar wind plasma to increase dramatically at the shock. Think of it this way. Imagine water from a faucet hitting a flat surface. The water comes out fast and thin, then suddenly spreads out into a slower, thicker, turbulent flow where it hits the surface. The point where the fast flow transitions to the slow flow is the shock. In the case of the heliosphere, the termination shock is a vast, three-dimensional surface surrounding the Sun at a distance of roughly 80 to 100 astronomical units, depending on the direction and the level of solar activity. Beyond the termination shock is the heliosheath. This is the region between the termination shock and the outermost boundary of the heliosphere. In the heliosheath, the solar wind is slow, compressed, and turbulent. It has been shocked and decelerated, but it is still solar wind, still composed of particles from the Sun, still carrying the Sun's magnetic field. The heliosheath is a thick, complex region, and as we will see, Voyager spent many years traversing it. The outermost boundary of the heliosphere is the heliopause. This is the surface where the pressure of the outward-flowing solar wind exactly balances the pressure of the inward-pressing interstellar medium. At the heliopause, the solar wind effectively stops. Beyond this boundary, the environment is dominated by interstellar particles and the interstellar magnetic field. Crossing the heliopause is crossing from the inside of the Sun's bubble to the outside. It is, in the most physically meaningful sense, leaving the Sun's domain and entering interstellar space. There may be one more boundary beyond the heliopause, the bow shock or bow wave. As the Sun moves through the interstellar medium at roughly 26 kilometers per second, the Sun is orbiting the galactic center and moving relative to the local interstellar gas. It may create a shock wave ahead of it, much like the bow wave of a boat moving through water. For years, this bow shock was depicted in textbook diagrams of the heliosphere. But more recent data, including measurements from the IBEX mission, suggests that the Sun may be moving too slowly relative to the interstellar medium to create a true shock. Instead, there may be a gentler bow wave, a region where the interstellar medium is slightly compressed and heated ahead of the heliosphere, but without a sharp shock transition. This is still an open question. The shape of the heliosphere is another area where Voyager data has overturned long-held assumptions. For decades, the standard picture was that the heliosphere is shaped like a comet, with a blunt nose pointed in the direction of the Sun's motion through the interstellar medium and a long tail streaming behind. This seemed intuitive. The interstellar medium should compress the heliosphere on the leading side and stretch it out on the trailing side, just as a comet's tail is shaped by the solar wind. But Voyager data, combined with measurements from the IBEX and Cassini missions, has challenged this picture. Some models now suggest the heliosphere might be more spherical than comet-shaped, while others propose exotic shapes, including one memorable model that described it as resembling a croissant. The shape depends sensitively on the strength and direction of the interstellar magnetic field, which interacts with the Sun's magnetic field at the heliopause in complex ways. The fact that Voyager 1 crossed the heliopause at a distance of about 121 astronomical units in one direction, while Voyager 2 crossed it at about 119 astronomical units in a different direction provides two data points. But two data points are not nearly enough to map the full three-dimensional shape of a structure that extends hundreds of astronomical units in every direction. Now, with all of this background in place, let us return to the Voyagers and follow their journey through these boundary regions. This is where the story gets truly extraordinary, where decades of patient waiting paid off in discoveries that rewrote the textbooks. After the planetary encounters, the Voyagers entered a long, quiet cruise phase. For years, and then decades, they flew through the outer solar system, measuring the solar wind, the magnetic field, and the cosmic ray environment. There were no dramatic planetary flybys, no stunning images, no front-page discoveries. The spacecraft just kept flying, their instruments patiently recording the slow, gradual changes in the space environment as they moved farther and farther from the sun. It was unglamorous work, the kind of science that does not make headlines but that builds, observation by observation, year by year, an invaluable record of conditions in regions of space that have never been sampled before. During this cruise phase, the power situation became increasingly critical. Each year, the RTGs produced about 4 fewer watts of electricity. Instruments were shut down one by one. Heaters that kept the spacecraft's components within their operational temperature ranges were turned off, and engineers held their breath to see if the instruments could continue to function at temperatures below their design specifications. Often, they could. The Voyager team became experts at coaxing performance from systems operating far outside their intended parameters. Every watt of power was precious, and the decisions about which instruments to keep and which to sacrifice were agonizing. Each instrument represented years of design and fabrication, the careers of scientists who had devoted their lives to the measurements it could make. Turning one off was like closing a window on the universe. But there was no choice. The plutonium was decaying, the power was dropping, and the mission had to continue with whatever instruments could still be supported. Then, in late 2004, something happened. After years of gradual changes, the instruments on Voyager 1 recorded a sudden, dramatic shift. On December 16, 2004, at a distance of approximately 94 astronomical units from the Sun, Voyager 1 crossed the termination shock. The solar wind speed, which had been gradually declining as Voyager moved outward, dropped precipitously. The magnetic field intensity increased. The temperature of the solar wind plasma spiked. Voyager had passed from the region of supersonic solar wind into the heliosheath, the slow, hot, turbulent region beyond the shock. This was the first direct detection of the termination shock by any spacecraft, and it immediately revealed surprises. The distance to the termination shock was not exactly what models had predicted. It was roughly where expected, but the precise location contained information about the pressure balance between the solar wind and the interstellar medium. More importantly, there were hints that the termination shock was not a stable, stationary surface, but a dynamic one, moving inward and outward in response to changes in the solar wind. There was evidence that Voyager 1 may have actually crossed the termination shock multiple times, as the shock moved back and forth, washing over the spacecraft like ocean waves washing over a beachgoer standing at the tide line. This dynamic behavior was expected by some models, but the details were new and important. There was a significant problem, though. One of Voyager 1's key instruments, the plasma science instrument, had stopped working way back in 1980 during the Saturn encounter. This instrument was designed to directly measure the properties of the solar wind plasma, its density, temperature, speed, and direction. Without it, Voyager 1 could not directly measure these critical plasma properties. It had to rely on indirect measurements from other instruments, the low-energy charged particle detector, the cosmic ray detector, and the magnetometer, to infer what the plasma was doing. This limitation would prove to be a major complication later, when Voyager 1 approached the heliopause, because without direct plasma measurements, determining exactly when Voyager had crossed the final boundary would be extraordinarily difficult. 3 years after Voyager 1's crossing, Voyager 2 reached the termination shock on August 30th, 2007, at a distance of approximately 84 astronomical units from the Sun. This was 10 astronomical units closer to the Sun than where Voyager 1 had crossed. The difference was significant and confirmed that the heliosphere is not symmetrical. The termination shock is closer to the Sun in the direction of Voyager 2's travel, roughly south of the ecliptic plane, toward the nose of the heliosphere, than in the direction of Voyager 1's travel, roughly north and somewhat to the side. The asymmetry is caused by the orientation of the interstellar magnetic field, which presses harder on the heliosphere in some directions than others. Voyager 2's termination shock crossing was in many ways more scientifically valuable than Voyager 1's, because Voyager 2's plasma science instrument was still working. This meant that for the first time, scientists had direct measurements of the solar wind plasma at the termination shock, and what they found was unexpected. The temperature of the plasma at the shock was much lower than predicted. The models had calculated how much the solar wind should heat up as its kinetic energy was converted to thermal energy at the shock, and the observed temperature was significantly below these predictions. Something was absorbing the energy that should have gone into heating the plasma. The answer, scientists deduced, was that a substantial portion of the kinetic energy of the solar wind was being transferred not into heat, but into accelerating a population of high-energy particles, what are called pickup ions and anomalous cosmic rays. The termination shock, it turned out, is a cosmic particle accelerator, converting the organized flow of the solar wind into the random high-energy motion of individual particles. This was a fascinating and important finding, because it showed that the boundary of the heliosphere plays an active role in energizing particles, a process that has implications for understanding how cosmic rays are accelerated throughout the universe. After crossing the termination shock, both the Voyagers entered the heliosheath and began the long traverse through this thick, turbulent region. Voyager 1 would spend 8 years in the heliosheath, from 2004 to 2012. Voyager 2 would spend even longer, from 2007 to 2018. During these years, the spacecraft sent back data that continually surprised and sometimes baffled scientists. One of the most important discoveries in the heliosheath was the revelation that the Sun's magnetic field, which extends outward through the solar wind and fills the heliosphere, does not smoothly transition from the inner heliosphere to the heliopause. Instead, in the heliosheath, the magnetic field breaks up into a frothy mess of magnetic bubbles. The traditional picture, based on models and theory, showed the Sun's magnetic field in the outer heliosphere as a series of smooth, nested, spiraling surfaces, like the layers of an onion. The reality was far more chaotic. Computer models incorporating Voyager's magnetic field data showed that the field lines in the heliosheath become unstable and break up into a foam of roughly spherical magnetic bubbles, each one about 100 million miles across. The heliosheath is not a smooth, orderly region, but a seething, bubbling chaos of magnetic structures. This has important implications for how cosmic rays penetrate the heliosphere, because the path a cosmic ray takes through this magnetic foam is very different from the path it would take through smooth, ordered magnetic field lines. As Voyager 1 moved through the heliosheath, it eventually entered a region that scientists had not predicted at all. Starting in mid-2012, the instruments began recording a peculiar combination of measurements. The intensity of cosmic rays from outside the heliosphere, galactic cosmic rays, began increasing dramatically. Simultaneously, the intensity of energetic particles from inside the heliosphere, particles accelerated by the sun and the termination shock began dropping rapidly. This was roughly what you would expect to see at the heliopause, the boundary between solar and interstellar domains. But the magnetic field, as measured by the magnetometer, did not change. It was still recognizably the sun's magnetic field, with the same general orientation and characteristics. This made no sense. If Voyager had crossed the heliopause, the magnetic field should have changed to the interstellar field, with a different strength and a different direction. But it had not. Scientists were deeply confused. Some argued that Voyager had crossed the heliopause and was in interstellar space, with the magnetic field discrepancy being explained by some as yet unknown process. Others argued that Voyager was still inside the heliosphere, in some new, unexpected region near the boundary. The debate was intense and sometimes heated. Papers were published arguing both sides. Press conferences were held in which NASA scientists carefully hedged their language, saying that Voyager was in a new region that had not been predicted by any model, but stopping short of declaring it was in interstellar space. The region was given the provisional name Heliospheric Depletion Region, or, more evocatively, the Magnetic Highway. The analogy was that the boundary between the heliosphere and interstellar space, rather than being a solid wall, was more like a highway, a region where particles could flow freely between the inside and the outside. Energetic solar particles could escape outward, while galactic cosmic rays could stream inward, but the magnetic field remained connected to the sun's. It was as if the door was open, but the walls were still standing. This region had not been predicted by any model, and its existence was a genuine surprise. It suggested that the heliopause is not a simple, sharp boundary, but a complex, layered transition zone with properties that depend on exactly how the solar and interstellar magnetic fields interact at that location. The breakthrough came in an unexpected way. In March 2012, a massive eruption on the sun, a coronal mass ejection, sent a shockwave of plasma hurtling outward through the solar system. This shockwave traveled at roughly the speed of the solar wind, much slower than light, so it took over a year to reach Voyager 1's location. When it arrived, in April 2013, it slammed into the plasma surrounding Voyager and caused it to vibrate, to oscillate at a specific frequency. Voyager 1's plasma wave instrument detected these oscillations, and from their frequency, scientists could calculate the density of the plasma surrounding the spacecraft. The calculation yielded a density of about 0.08 electrons per cubic centimeter, roughly 40 times higher than the typical density of the solar wind in the heliosphere. This was the density expected for the interstellar medium. It was the smoking gun. Voyager 1 was surrounded by interstellar plasma. It was in interstellar space. Working backward from this measurement, scientists determined that Voyager 1 had crossed the heliopause on August 25, 2012, at a distance of approximately 121.6 astronomical units from the Sun. On that date, the cosmic ray and energetic particle measurements had shown the sharp transition that marked the boundary, even though the magnetic field had not changed as expected. The announcement was made at a NASA press conference on September 12, 2013, and it was one of the most momentous announcements in the history of space exploration. For the first time, a human-made object had left the heliosphere and entered interstellar space. Voyager 1 had reached the edge of the solar system, in the heliospheric sense, and crossed it. But the mystery of the magnetic field remained. Why did the magnetic field not change direction at the heliopause? If the interstellar magnetic field has a different orientation than the Sun's magnetic field, as all models predicted, then Voyager should have detected a change in the magnetic field direction when it crossed from one to the other. But it did not. The field direction changed only slightly. Several explanations have been proposed. One possibility is that the interstellar magnetic field, at least in the immediate vicinity of the heliopause, has been draped and distorted by its interaction with the heliosphere, aligning it partially with the solar magnetic field. Another possibility is that the two fields are, by coincidence, roughly aligned in this particular direction. A third possibility involves magnetic reconnection at the heliopause, a process where solar and interstellar field lines break and reconnect, creating a mixed field region near the boundary. None of these explanations is fully satisfying, and the magnetic field puzzle remains one of the most important unresolved questions from Voyager's heliopause crossing. 6 years later, on November 5, 2018, Voyager 2 crossed the heliopause at a distance of approximately 119 astronomical units from the Sun. This was a historic moment not just because it confirmed Voyager 1's crossing, but because Voyager 2 still had its working plasma science instrument. For the first time, scientists had direct measurements of the plasma on both sides of the heliopause, taken by the same type of instrument on the same type of spacecraft. The data was extraordinary. Voyager 2's plasma instrument showed that the crossing was remarkably abrupt. The solar wind plasma density, temperature, and speed all changed sharply over a very short distance, less than the spacecraft traveled in a single day. The interstellar plasma on the other side was denser, cooler, and moving more slowly than the solar wind plasma on the inside. The heliopause was a real, defined boundary, not a gradual transition. Voyager 2's crossing also revealed some interesting differences from Voyager 1's. Because Voyager 2 was crossing the heliopause in a different direction, in the southern hemisphere of the heliosphere rather than the northern, the details of the crossing were somewhat different. The magnetic field did change more at Voyager 2's crossing than at Voyager 1's, though still not as dramatically as some models had predicted. And there was a fascinating detail. Just before crossing the heliopause, Voyager 2's plasma instrument detected interstellar plasma leaking into the heliosphere. The boundary was not perfectly sealed. There was a trickle of interstellar material getting in before Voyager 2 had fully crossed out. This leakage might occur through small-scale structures in the heliopause, regions where magnetic reconnection or other processes create temporary gaps in the boundary. Now, both Voyagers were in interstellar space, sending back measurements from a region that no human instrument had ever sampled. And what they found there was not what anyone expected. If you are still with me at this point, if you have followed the Voyager story from its launch through the grand tour of the planets and across the boundary of the heliosphere into interstellar space, then you are a true explorer in every sense that matters. You have the curiosity and the patience and the hunger for understanding that drives all great discovery. Drop a rocket emoji in the comments right now because you have earned it. And before I tell you what Voyager found in interstellar space, let me ask you, what do you think it is like out there? Do you think interstellar space is empty, silent, dark? Or do you think there is something more? Hold that thought, because the answer is going to surprise you. The first and most fundamental thing to understand about interstellar space is that it is not empty. This is one of the most persistent misconceptions about space. When we say the vacuum of space, we conjure images of absolute nothingness, a perfect void with nothing in it. And it is true that interstellar space is extraordinarily thin by any everyday standard. The density of particles in the interstellar medium near the Sun is roughly 0.05 to 0.1 particles per cubic centimeter. That means in a volume of space the size of a sugar cube, you would find, on average, less than one particle. By comparison, the air you are breathing right now contains roughly 25 billion, that is 2.5 times 10 to the 19th power, molecules per cubic centimeter. Interstellar space is unimaginably empty compared to our everyday experience. But it is not nothing, and the particles that are there, sparse as they are, have properties that carry enormous amounts of information about the history and structure of the galaxy. The interstellar medium near the Sun is a partially ionized gas, a mixture of ions, electrons, and neutral atoms, primarily hydrogen and helium. The Sun is currently traveling through a region called the Local Interstellar Cloud, or LIC, a relatively warm, relatively tenuous cloud of interstellar gas that is about 30 light-years across. The temperature of the LIC is roughly 6,000 to 7,000 Kelvin, which sounds hot, but remember that temperature in a gas is a measure of the average kinetic energy of the particles. And when the density is incredibly low, a high temperature means the particles are moving fast, but there are so few of them that you would not feel any heat. It is like the difference between a spark from a campfire, which has a temperature of thousands of degrees but carries so little energy that it does not burn you, and a pot of boiling water, which is only at 100 degrees but contains enough energy to cause serious harm. The local interstellar cloud is one of several clouds of gas that the Sun passes through as it orbits the center of the Milky Way galaxy. The Sun completes one orbit around the galactic center roughly every 225 to 250 million years, a period sometimes called a galactic year, moving at about 230 kilometers per second. As it orbits, it encounters different environments, denser clouds, thinner voids, regions of higher or lower magnetic field strength, regions heated by nearby supernovae or cooled by radiative processes. The interstellar medium is not uniform. It is a complex, dynamic, structured environment shaped by the life cycles of stars, the explosions of supernovae, the winds of massive stars, and the overall dynamics of the galaxy. Voyager's instruments are sampling this environment directly for the first time, and one of the most striking discoveries was the detection of a persistent, low-frequency plasma wave emission, a steady, narrowband signal that scientists have described as a hum. This hum was first reported in 2021, based on analysis of Voyager 1's plasma wave data. The signal is incredibly faint and narrow in frequency, and it appears to be present continuously in the background, underneath the louder, more transient signals caused by solar shock waves passing through the interstellar medium. When a solar eruption sends a shock wave outward from the Sun, and that shock wave eventually reaches Voyager's location in interstellar space, which takes more than a year given the distance, it causes the interstellar plasma to vibrate intensely, producing loud, easy-to-detect plasma oscillations. But in between these events, in the quiet intervals when no solar shockwave is passing by, Voyager still detects a faint, steady oscillation. This is the hum. The hum tells scientists something profound about the interstellar medium. Its frequency is directly related to the density of the surrounding plasma, and the steady nature of the hum indicates that the baseline density of the interstellar medium in Voyager's neighborhood is remarkably stable and uniform, at least on the scales that Voyager can probe. The density indicated by the hum is roughly 0.055 electrons per cubic centimeter, consistent with expectations for the local interstellar cloud. But the fact that it is so steady, so persistent, and so narrowband suggests that the interstellar medium, at least in this particular region, is surprisingly calm and uniform between solar-driven disturbances. It is the background music of the galaxy, a gentle oscillation that has been playing for billions of years, unheard by anyone until a small spacecraft from a small planet carried a sensitive instrument into the void between the stars and finally detected it. The cosmic ray environment in interstellar space was another major area of investigation. Inside the heliosphere, the Sun's magnetic field acts as a partial shield against galactic cosmic rays. high-energy particles that originate from supernovae, neutron stars, and other energetic phenomena throughout the galaxy and beyond. These cosmic rays are constantly bombarding the heliosphere from all directions, but the solar magnetic field deflects many of them, particularly the lower energy ones, preventing them from reaching the inner solar system and Earth. The degree of shielding varies with the solar cycle. During periods of high solar activity, when the solar magnetic field is stronger and more complex, the shielding is more effective, and fewer cosmic rays reach Earth. During solar minimum, the shielding weakens, and the cosmic ray flux at Earth increases. This variation has been measured on Earth for decades using neutron monitors and other instruments. When Voyager crossed the heliopause, it left the protective magnetic shield of the heliosphere and was exposed to the full, unshielded flux of galactic cosmic rays. The cosmic ray intensity detected by Voyager jumped significantly at the boundary, increasing by roughly 9% at Voyager 1's crossing. This might not sound like a dramatic increase, but remember that the heliosphere only blocks a fraction of the cosmic ray flux, primarily the lower energy cosmic rays that are most easily deflected by magnetic fields. The higher energy cosmic rays, which are barely affected by the heliosphere's magnetic field, were already being detected deep inside the heliosphere. What Voyager measured at the heliopause was the unmasking of the lower energy component of the galactic cosmic ray spectrum, particles that had been blocked from the inner heliosphere by the solar magnetic field. The intensity and energy spectrum of these cosmic rays carry information about their origins and about the structure of the interstellar magnetic field through which they have traveled. Cosmic rays are produced by some of the most violent events in the universe: supernova explosions, the powerful jets of active galactic nuclei, the collisions of galaxy clusters, and possibly even more exotic sources. They have been traveling through the galaxy for millions of years, bouncing off magnetic field irregularities, gradually losing energy, and being deflected from their original paths. By the time they reach our neighborhood, their directions are thoroughly randomized, and they appear to come from all directions roughly uniformly. But the detailed energy spectrum, the distribution of how many cosmic rays there are at each energy level, encodes information about their sources and their journey. Voyager's measurements of the cosmic ray spectrum outside the heliosphere are the first unshielded measurements ever made and provide a crucial baseline for understanding galactic cosmic rays. There was another cosmic ray surprise. As Voyager 1 moved deeper into interstellar space after crossing the heliopause, the cosmic ray intensity continued to increase very slowly. This was unexpected. If Voyager had simply left one uniform region, the heliosphere, and entered another uniform region, the interstellar medium, the cosmic ray intensity should have leveled off quickly after the crossing. The continued slow increase suggested that even outside the heliopause, the heliosphere's influence on the cosmic ray environment extends some distance. This makes sense physically. The heliosphere acts as a barrier to cosmic rays, and in the immediate vicinity of the heliopause, the cosmic ray intensity is slightly depleted because cosmic rays approaching from the far side have been partially blocked by the heliosphere. Farther from the heliopause, this shadowing effect diminishes, and the cosmic ray intensity approaches its true interstellar value. Voyager is, in a sense, emerging from the heliosphere's cosmic ray shadow, and has not yet fully emerged from it. The plasma density measurements in interstellar space have revealed another intriguing puzzle. As Voyager 1 has moved farther from the heliopause, the plasma density has not remained constant. Instead, it has shown a gradual increase with distance. Voyager 2, crossing the heliopause in a different direction, also detected increasing density with distance, though the detailed profile is different. Several explanations have been proposed for this density gradient. One possibility is that the heliosphere is plowing through the interstellar medium, compressing the gas ahead of it like a snowplow compresses snow, creating a region of enhanced density near the heliopause that gradually returns to the background level farther away. This is the hydrogen wall, or pile-up region that had been predicted by some models. Another possibility is that there are natural density variations in the interstellar medium, features in the local interstellar cloud that happen to produce a density gradient in the direction of Voyager's travel. A third possibility involves the interaction between neutral atoms and ions in the interstellar medium, a process called charge exchange that can create density enhancements near the heliopause. Distinguishing between these possibilities requires more data, and Voyager continues to collect density measurements as it moves farther into interstellar space. The temperature of the plasma at and near the heliopause was another surprise. Models had predicted a certain temperature for the interstellar plasma near the boundary, based on the thermodynamics of how the solar wind interacts with the interstellar medium. The observed temperature was higher than predicted, roughly 30,000 to 50,000 Kelvin, compared to the 6,000 to 7,000 Kelvin expected for the undisturbed local interstellar cloud. This excess heating must come from somewhere, and several mechanisms have been proposed. The compression of interstellar material by the heliosphere could heat the plasma, analogous to how air heats up when compressed by a bicycle pump. Energy from the termination shock could be conducted outward through the heliosheath and into the interstellar medium. Magnetic reconnection at the heliopause, where solar and interstellar magnetic field lines break and reconnect, could release energy that heats the plasma. And there may be heating from the dissipation of waves and turbulence generated by the interaction of the heliosphere with the interstellar medium. Untangling these mechanisms is an ongoing challenge. In 2020, a team of scientists combined data from Voyager and several other missions to calculate the total pressure of particles in the outer heliosphere and nearby interstellar space. They added up the thermal pressure from the random motion of particles, the magnetic pressure from the interstellar magnetic field, and the cosmic ray pressure from the energy of high-energy particles. The total pressure they calculated was higher than expected, and there appeared to be a component of pressure from a previously unaccounted-for population of energetic particles. This suggests that our inventory of what exists in the interstellar medium near the heliosphere is not complete. There is something contributing to the pressure that we have not fully identified or measured. It might be a population of superthermal particles, ions with energies between the thermal plasma and the high-energy cosmic rays, that Voyager's instruments are not well suited to detect. It might be related to the heating mechanism that produces the excess temperature. Whatever it is a reminder that even with 2 spacecraft in interstellar space, we are still only scratching the surface of understanding this environment. Let me pull back from the detailed observations for a moment and talk about what all of this means in a larger context, because the significance of Voyager's discoveries extends far beyond the specific measurements of plasma density and cosmic ray flux. These discoveries tell us something profound about our place in the cosmos and about the conditions that make life on Earth possible. The heliosphere is not just an abstract astrophysical structure. It is a shield. It is the thing that stands between us and the full fury of the galaxy's energetic particle environment. Inside the heliosphere, the Sun's magnetic field deflects a substantial fraction of the galactic cosmic rays that would otherwise bombard Earth. These cosmic rays are not just a curiosity for physicists. They are subatomic bullets that can penetrate deep into matter, breaking molecular bonds, damaging DNA, and causing mutations. On Earth's surface, we are further protected by the planet's own magnetic field and by the atmosphere, which absorbs most of the cosmic rays that make it through the heliosphere. But even so, galactic cosmic rays are responsible for a significant fraction of the background radiation dose that all living things receive, and they are a major concern for astronauts and for the electronics in satellites and spacecraft. The heliosphere blocks roughly 70% of the galactic cosmic rays that approach the solar system. Without this shielding, the radiation environment at Earth's surface would be significantly more intense, and the rate of DNA damage in living organisms would be measurably higher. Over geological time, variations in the heliosphere's shielding could have had profound effects on life. During periods of unusually low solar activity, when the heliosphere weakens and more cosmic rays penetrate to Earth, there is some evidence of increased cloud formation. Cosmic rays may play a role in nucleating cloud droplets, which could affect climate. Some researchers have even speculated about a connection between cosmic ray flux and mass extinction events, though this remains highly controversial, and the evidence is far from conclusive. What is not controversial is that the heliosphere matters for life, and Voyager is giving us the first direct measurements of how this shield works, how it interacts with the interstellar environment, and how effectively it blocks cosmic rays. This information is crucial, not just for understanding our own planet's history, but for assessing the habitability of planets around other stars. Every star that has a wind creates its own version of a heliosphere, called an astrosphere. The size and effectiveness of an astrosphere depend on the strength of the stellar wind, which in turn depends on the star's type, age, and activity level. Red dwarf stars, which are the most common type of star in the galaxy, and which host many of the exoplanets we have discovered, may have relatively weak astrospheres that provide less cosmic ray shielding than our Sun's heliosphere. If this is the case, then planets around red dwarfs, even those in the so-called habitable zone where liquid water can exist, might be bathed in much higher cosmic ray fluxes than Earth, potentially affecting their habitability. Voyager's measurements of our own heliosphere provide the ground truth, the calibration data, for all models of stellar astrospheres and their effects on planetary habitability. There is another dimension to this that is even more mind-bending. The Sun is not stationary. It is moving through the galaxy, and as it moves, it encounters different regions of the interstellar medium. Right now, the Sun is passing through the local interstellar cloud, which has a particular density, temperature, and magnetic field. But the Sun entered the local interstellar cloud relatively recently in astronomical terms, perhaps tens of thousands of years ago, and it may be approaching the edge of this cloud, about to enter a different region of interstellar space with different properties. When the Sun enters a denser region of interstellar medium, the increased pressure will compress the heliosphere, making it smaller and reducing its cosmic ray shielding capability. When the Sun enters a less dense region, the heliosphere will expand and the shielding will improve. These variations have occurred throughout the solar system's history and will continue to occur. During particularly dense encounters, the heliosphere might have been compressed so much that the Earth found itself at or near the heliopause, essentially unshielded from galactic cosmic rays. Such events would have had significant effects on the planet's radiation environment and potentially on its biosphere. Some scientists have proposed that the Sun's passage through the spiral arms of the Milky Way, which occurs roughly every 100 million years or so, might expose the solar system to denser interstellar environments and higher cosmic ray fluxes, with possible connections to mass extinction events and ice ages on Earth. The timing is roughly right for some correlations, but the evidence is circumstantial and the mechanisms are not fully understood. What is clear is that the interaction between the heliosphere and the interstellar medium, the interaction that Voyager is measuring directly for the first time, has real, tangible consequences for conditions on Earth over geological time. Voyager's data also has implications for understanding the interstellar medium itself as a record of galactic history. The particles that Voyager is sampling in interstellar space did not originate in our solar system. They come from elsewhere in the galaxy. The cosmic rays were accelerated by distant supernovae, neutron stars, and other high-energy phenomena. The plasma was ejected from ancient stars and processed by galactic dynamics over billions of years. The dust particles, too small for Voyager to detect individually but present in the interstellar medium, are the detritus of stellar evolution, the ashes of stars that lived and died before our sun was born. Every measurement Voyager makes in interstellar space is, in a sense, a measurement of galactic history, a reading of the galaxy's ongoing story written in particles and fields. Now, let us come back to the present and talk about where the Voyagers are right now, what condition they are in, and how much longer they can continue their mission. Because this is a race against time, and the clock is ticking. As of the current time, Voyager 1 is the most distant human-made object in existence. It is approximately 165 astronomical units from the Sun, a number that increases by roughly 3.6 astronomical units every year. Its radio signals, traveling at the speed of light, take more than 22 hours to reach Earth. Voyager 2 is somewhat closer, at approximately 140 astronomical units from the Sun, its signals taking more than 18 hours to reach Earth. Both spacecraft are heading out of the solar system in different directions. Voyager 1 is heading generally toward the constellation Ophiuchus, while Voyager 2 is heading toward the constellation Sagittarius. They are diverging from each other and from the Sun with every passing second. The communication link with the Voyagers is maintained by NASA's Deep Space Network, the collection of large radio antennas in California, Spain, and Australia. The data rate from the Voyagers is painfully slow by modern standards, about 160 bits per second. To put that in perspective, a typical home internet connection might operate at 100 million bits per second or more. Voyager is transmitting data at a rate roughly 600,000 times slower than your home internet. At this rate, sending a single smartphone photo from Voyager would take several hours. But the data Voyager sends, slow as it is priceless. Each bit of information represents a measurement from a region of space that no other instrument can reach, a unique window on a part of the universe that we can study in no other way. The power situation is the most critical factor determining how long the Voyagers can continue. The RTGs have been losing power steadily for almost 5 decades, and by now they are producing roughly 200 to 220 watts of electricity, down from 470 at launch. This is not even enough to power 2 standard household light bulbs, and the power loss continues, about 4 watts per year. Every few years, the mission team has to make the difficult decision to turn off another instrument or heater to keep the remaining instruments within their power budget. The decisions about which instruments to keep are guided by a simple principle: prioritize the measurements that can only be made in interstellar space. The instruments that are still operating include the magnetometer, the cosmic ray detector, the low-energy charged particle detector, and the plasma wave instrument. These are the instruments that are making the groundbreaking measurements in interstellar space. The magnetic field, the cosmic ray flux, the energetic particle environment, and the plasma density and wave activity. Other instruments, including the cameras, turned off long ago, the infrared spectrometer, the ultraviolet spectrometer, and the photopolarimeter, have been turned off to conserve power. The temperature management situation is equally dire. Many of the spacecraft's components were designed to operate within specific temperature ranges, and heaters were used to keep them warm enough to function. As power has declined, heaters have been turned off, and some instruments and spacecraft components are now operating at temperatures well below their designed minimums. The fact that they continue to work is a testament to the engineering margins built into the original design and to some extent to good fortune. But each winter, as the spacecraft continue to cool, there is a risk that some component will drop below its functional temperature limit and fail. There is also the matter of the spacecraft's aging electronics. The computers, the memory systems, the communication hardware, all of these are over 45 years old and have been operating continuously in an environment of cosmic radiation and extreme temperatures. In 2023, Voyager 1 began transmitting garbled, meaningless data instead of the expected telemetry. The engineering team at JPL diagnosed the problem as a fault in the flight data subsystem's memory, specifically a malfunctioning memory chip that was corrupting the data before transmission. The challenge of fixing this problem was extraordinary. The spacecraft is so far away that each command from Earth takes over 22 hours to arrive, and the confirmation of its receipt takes another 22 hours to come back. Diagnosing the problem, developing a fix, testing it, transmitting it, and verifying it all had to be done with this 44-hour round-trip delay. There was no possibility of trial and error in real time, no ability to reboot and see what happens right away. Every command had to be meticulously planned and verified before transmission. The engineering team devised an ingenious solution. They rerouted the flight data system's code around the faulty memory chip, storing the affected code segments in other healthy parts of the spacecraft's memory. The process took months. The fix was transmitted in stages, each one carefully verified before the next was sent, and it worked. Voyager 1 resumed sending coherent data. This remote repair of a computer more than 15 billion miles away, performed with the patience and precision of a surgeon operating by mail, is arguably one of the most impressive feats of engineering in human history. It is a testament to the skill, dedication, and ingenuity of the Voyager team, many of whom have worked on the mission for their entire careers. How much longer can the Voyagers continue? The most optimistic estimates suggest that at least some instruments can be kept running until the early to mid-2030s. The most pessimistic estimates suggest that the power situation could force a complete shutdown sooner. The engineering team is constantly looking for ways to extend the mission, turning off additional heaters, reducing the power consumption of the remaining instruments, finding clever software tricks to squeeze more efficiency from the dwindling power supply. Every additional year of data from interstellar space is enormously valuable, because these are measurements that no other existing or planned spacecraft can make. Eventually, probably sometime in the 2030s, the power will drop below the level needed to operate any scientific instrument. The last instrument will be turned off, and Voyager will stop collecting data. But even then, the spacecraft may not go completely silent immediately. The transmitter might continue to operate for some time after the last instrument is shut down, sending a carrier signal without any data, a kind of electronic heartbeat that simply says, "I am still here." And eventually, even the transmitter will fall silent, and Voyager will continue its journey in silence, a ghost ship in the void between the stars. But silence is not the same as stopping. Even after it goes silent, Voyager will keep moving. There is nothing in interstellar space to slow it down significantly. No air resistance, no friction, no substantial gravitational force. The gravitational influence of individual stars at these distances is negligible over the distances Voyager will travel in the near term. Voyager 1 will continue on its current trajectory, moving at about 17 kilometers per second relative to the Sun, heading outward into the galaxy, essentially forever. Where is it going? What will it encounter in the eons to come? The answers are both specific and staggering. In about 300 years, Voyager 1 will reach the inner edge of the Oort cloud, if it exists as theorized. The Oort cloud is the most remote region of the solar system, a vast spherical shell of trillions of icy bodies left over from the formation of the solar system, extending from roughly 2,000 astronomical units to perhaps 100,000 astronomical units from the Sun. These icy bodies are the source of long-period comets, the comets that appear in the inner solar system on orbits that take thousands or millions of years to complete. The Oort cloud has never been directly observed. Its existence is inferred from the orbits of long-period comets and from theoretical models of solar system formation. Voyager will pass through the Oort cloud without detecting it, because its instruments will have been dead for centuries by then, and because the individual objects in the Oort cloud are so small and so widely separated that the probability of Voyager passing close to one is essentially zero. It will take Voyager roughly 30,000 years to traverse the Oort cloud. 30,000 years. That is longer than the entire span of recorded human history. When Voyager enters the Oort cloud, it will still technically be within the Sun's gravitational domain. When it exits the Oort cloud, it will truly be free of the Sun, an interstellar wanderer with no gravitational allegiance to any star. In about 40,000 years, Voyager 1 will make its closest approach to another star, AC plus 793888, also known as Gliese 445, a star in the constellation Camelopardalis. At closest approach, Voyager will pass within about 1.6 light-years of this star. This is still an enormous distance, about 10 trillion kilometers, but it is the closest Voyager 1 will come to any star for a very long time. Gliese 445 is a red dwarf star, small and dim, unremarkable in every way except that it will be briefly the nearest star to our most distant emissary. Voyager 2, on its different trajectory, will pass within about 4.3 light-years of Sirius, the brightest star in the night sky, in about 296,000 years. On truly astronomical timescales, the Voyagers will orbit the center of the Milky Way galaxy, along with all the other stars and material in the galaxy. Their orbits will be slightly different from the Sun's, because they were launched with a velocity relative to the Sun, so they will gradually drift away from the Sun's galactic orbit. But the general trajectory will be a slow, lazy orbit around the galactic center, taking hundreds of millions of years to complete. The Voyagers will circle the galaxy for billions of years, unless they happen to pass close enough to a star or other massive object to be gravitationally captured or deflected, which is extremely unlikely given the vast distances between stars. And all the while, they will carry the golden record. The record is made of gold-plated copper, one of the most durable materials available. In the near-perfect vacuum of interstellar space, with no atmosphere to cause corrosion, no water to cause erosion, no biological organisms to cause decay, the golden record will be extraordinarily durable. Cosmic rays will slowly degrade the material over time, breaking molecular bonds in the coating and the substrate, but the process will take billions of years to cause significant damage. The images and sounds and music encoded on the record will remain readable, at least in principle, for an almost incomprehensible span of time, far longer than our sun will continue to shine, far longer than Earth will remain habitable, far longer perhaps than the human species will exist. The golden record is the most enduring artifact of human civilization. It will survive when everything else we have built has crumbled to atoms. The pyramids, the Great Wall, the cathedrals and skyscrapers and cities, all of these will be dust and less than dust, recycled by geological processes and scattered by the winds of deep time. But the golden record will still be out there, drifting silently between the stars, carrying the sounds of Bach and Beethoven and Chuck Berry, the greetings of the children of Earth, the brainwaves of a woman falling in love, the message of a species that looked up at the stars and decided to introduce itself. Will anyone ever find it? The honest answer is, almost certainly not. The chance of a random encounter in the vast emptiness of interstellar space is vanishingly small, so small that it is barely distinguishable from zero. The Voyager spacecraft are heading in specific directions, but specific direction loses all meaning over the timescales and distances involved. The stars that Voyager will approach most closely are moving too, and in 40,000 years the entire stellar neighborhood will have rearranged itself. And even if an alien civilization did detect Voyager's approach, which would require technology far beyond our own to detect such a tiny, cold, dark, silent object against the background of interstellar space, the chances that they would recognize it as an artificial object, retrieve it, figure out how to play the record, and successfully decode the information on it are, well, let us just say they would need to be very clever. But as Carl Sagan said, the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. The golden record was never about the aliens. It was about us. It was about what we choose to send out into the universe when we have the chance, about what we consider worth preserving and sharing, about how we define ourselves when we imagine speaking to the cosmos. And by that measure, the golden record is one of the most beautiful and profound things humanity has ever created. Let us now turn our attention to the future, to the missions that will build on Voyager's legacy and explore the heliosphere and interstellar space with the tools and capabilities of the 21st century. Voyager was not designed to study the heliosphere. Its heliospheric and interstellar discoveries are a bonus, the result of a mission that dramatically outlived its original purpose and happened to be in the right place at the right time with the right instruments. A dedicated mission to the heliosphere and interstellar space, designed from the ground up for this specific purpose, could achieve enormously more. And such a mission has been proposed.